to make you a quick Friday?
Our third part of the semester by addressing the issue of how to create a self-sustained chain reaction. And this is a topic of reactor theory in general. And we know that the fission process is generated or controlled by neutrons. So we start our lectures by studying how neutrons interact with matter. Then we derive the expression for the theory with which neutrons interact with matter, which is the diffusion theory or neutron diffusion theory. We will consider two types of systems. One system in which multiplication through fission by the neutrons occur, and we'll call this the neutron multiplication theory. In that case, we also talk about criticality, how to create a critical configuration like in the Chicago pile number 1 and in all existing nuclear reactors. But we also are concerned about how neutrons interact with matter from the perspective of shielding against radiation that originates with neutrons. Neutrons is not going to be the only radiation present, because it interacts with material generating gamma radiation or electromagnetic radiation, and we have to shield personnel against both of them. But also neutrons have a useful application in neutron cancer therapy. So we can destroy tumor cells by using also neutrons. So our emphasis right now, we have only 2 weeks left in the semester, so we'll try to squeeze as many lectures concerning neutrons and criticality, and maybe have some time to look at fusion energy too. So this is the plan for the rest of the semester. We share the screen, and we go to the chapter on neutron interactions with matter under the transport and diffusion reactor theory. We are going to bypass transport theory and subcritical assembly theory. I invite you to read them on your own, but we go directly to the chapter on neutron cross-sections. Neutron cross-sections is going to be our way of studying how neutrons interact with matter. Neutrons' interaction with matter can either be scattering or absorption reactions. Remember, neutrons do not interact with the electronic cloud, so it is not atomic interactions. A neutron interacts directly with the nucleus. And we know that the nucleus is carrying most of the mass of the atom. The electrons are 1/800th the mass of the hydrogen atom. So you could see that the mass of all the nuclei, all the atoms around us are really concentrated in the nucleus. So neutrons do not see the negative electronic cloud around the nucleus in the atom, and they interact directly with the nuclei. As they interact with the nuclei, they can either be scattered, like a ball bouncing off a wall, so they scatter, or they can also be absorbed. And if they are absorbed, many different reactions can occur. Like fission can occur, absorption with the emission of a gamma photon can occur, transmutations in general also occur in general. Scattering can result in the change in both the energy of the incoming neutrons. So in that case, we can thermalize neutrons, brings them down from their fission energy, 2 million electron volts, all the way down to the kT energy, K Boltzmann constant, T the Kelvin degrees. In that case, they can be in thermal equilibrium with the medium. And we'll see that in that case, they have a higher probability of interaction with the nucleus. An interesting aspect of neutrons is that bound neutrons, the neutrons that exist in the cells in our body or all the materials surrounding us, neutrons are stable. But free neutrons, like what happens in a nuclear reactor, are unstable. In fact, they have a half-life of 10 minutes. So within 10 minutes, free neutrons would decrease in their number to 1/2 the original amount. So that's some kind of a holy grail of modern physics. So we do not know how to explain that a free neutron is unstable. It turns into a proton and an electron as it decays. So it's radioactive, you want to call it. And but bound neutrons are definitely stable. Otherwise, the whole universe would be disintegrating into electrons and protons in general. Absorption can lead to the formation of different nuclei. So neutrons are the scalpel by which we can create or modify the nature of the nuclei. Remember, in nuclear reactions, we conserve mass, energy, nucleons, and charge. And in that case, we can create new species or transmute different nuclei from one chemical form to another by manipulating the isotopes. The probability or the description on how these different types of reactions occur are mostly empirical with some theory added to it. And it depends on the energy of the neutrons. And we describe that by what we call the cross-section. The cross-section is the effective area that the nucleus presents to the nucleus as it interacts with it. And we show the cross-section. It's an area, but we'll define the unit for it as the bond in a moment. People who measure those cross-sections simply were joking. It's a very, 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 very small, tiny area for each nucleus. But jokingly, the people who spend their really careers measuring those cross-sections for us to use in designing nuclear reactors and shields against radiation, they give it the name, the area in a unit that is a barn. And you know, a barn is where animals are kept and the barns are very, very large. So they took something very, very tiny and they gave it the name of something very large. This is the probability of interactions as a function of energy of neutrons with the isotope of plutonium 239. And some interesting observation is seen here is that when we have high energy of the neutrons, the cross-section is lower than when the neutron energy is very low. You could see here if this is a logarithmic scale, it goes into decades, factors of 10. Here is 1, 10, 100, 1,000. You could see here that the cross-section at low energy of the neutron, say at thermal energy 0.025 electron volt, this is the unit we are going to use here, I found that it's 1,000 bonds. However, at high energy, oh, it's only 10 bonds. So it's a factor of 100 at low energy. And that's why we moderate the energy of the neutrons. We use a moderator. That was the genius of Enrico Fermi in the Chicago Pi #1, is that he moderated the neutrons to reach thermal energies with graphite, with collision, the neutrons colliding with the nuclei. Notice here, these are measured cross-sections as a function of the energy of the neutrons. We have different reactions possible, like one describes the fission process. One describes, say, the elastic scattering. One described the inelastic scattering. Elastic means that there is no change in the excitation energy of the nucleus. Inelastic means that the nucleus is excited and eventually emits a gamma radiation. Capture is when the neutron is totally absorbed in the nucleus, and fission obviously is when the neutron fissions the nucleus. When we add all those interactions together, we come up with the total cross-section shown on the top right here. It is very obvious that there is what's called here a resonance. So the resonance here tells us that at a certain energy here of the neutrons, the reaction rate is not just 1,000, the cross-section is not just 1,000 bonds, but it's maybe 7,000 or 8,000 bond. So this is a resonance in the same as happen in a tuning circuit in electronics when you change the resistance, the capacitance, and the inductance, and of course tune up your radio or your TV to a certain wavelength. So at that point here, there is a susceptibility for the reaction to be higher than around the resonance. And that tells us that the neutrons, in fact, are interacting more like a wave rather than interacting like a particle. So in that case, the ideas of wave mechanics and quantum mechanics do apply. This is not the only resonance in the cross-section where the cross-section reaches a very high value. You notice here, these are all different resonances in the range of 10 to 1 kilo electron volt or 1,000 electron volt. This is called the resonance region. And in that resonance region, a neutron that is born here, like that's 1 million electron volt, 2 million electron volt is the energy at which a neutron is born from fission. As it slows down, as it loses energy, it reduces its energy, it reduces its energy, it reduces its energy. And in that spot here, in that area of energy, it can be absorbed in the nucleus. So in that case, if you use a slurry of uranium with a moderator, graphite, or heavy water, that's what the Germans tried in the Second World War, the neutron gets absorbed in that resonance region and can never reach that thermal region where it can cause fission. Again, the genius of Enrico Fermi is that he separated the uranium. Remember, he had balls of uranium inside bricks of graphite. So in that case, when the neutron is born from fission, it has a chance to lose its energy by interacting with the graphite without encountering a nucleus of uranium-238 and get absorbed. So in that case, there is a probability that it escapes the resonance region. And in the four-factor formula that we derived for the Oklo phenomenon, we had a term that described the multiplication of the neutrons as the resonance escape probability in our case. Now, these are all cross-sections that are measured. We cannot use, obviously, these in calculations. So people who measure those cross-sections try to help us by creating what is called evaluated cross-section. So in that case, they divide the energy region into little segments or different range. They have a name for them, groups of energy, and they present us databases where we can use those ranges of energy or group cross-sections for making calculations of the criticality or design of different reactors. This is called now the group average, total elastic, inelastic fission, and capture cross-sections. The data here can be obtained from the chart of the nuclides under a legend that gives us basically those graphs of cross-sections. Now we have to address the issue of that area. How do we measure that area? A nucleus area is very, very small. An atomic, an atom also, dimensions are very small. If you think about the dimension of the atom, that is in the range of the angstrom, which unit which is used for measuring wavelengths, and that's 10 to the minus 8 centimeter, 100 million centimeter. We cannot, of course, measure it directly, but we infer it from experimentation. The nucleus, on the other hand, is even smaller than the atom itself, and it occupies 1/10,000th the characteristic length of the atom. So you'll find that a nucleus occupies characteristic length is 10 to the minus 12 centimeter. If you give it an analogy, that would be like a football in the middle of a football field. So you could see that what we see as objects are primarily really light interactions with the atomic structure of our nuclei in the environment around us. So because the the characteristic length of the nucleus is 10 to the minus 12 centimeter. If you square that number, you get an area. So 10 to the minus 12 squared is 10 to the minus 24, and that becomes centimeter squared. And the people who measured those cross sections simply jokingly called it the barn. So the unit of the barn here, the cross section, is a unit of an area that is 10 to the minus 24 centimeter squared. This is the effective area of the nuclei through our observations and experimentation in general. So try to remember that unit. You notice that the cross sections are plotted on a log-log scale, meaning that the y-axis is a natural logarithmic scale. You could see here for each decade or each factor of 10, you can find 1/3 of the way you get the 2, and 2/3 of the way you get the 5. So if you read here, this is 1, that would be 2, and 2/3 of the way you can really draw a logarithmic scale by hand by taking 2 here and then 5 2/3 of the way. So logarithmic scales are used when you have a very, very large range. We cannot use a linear scale. We use a logarithmic scale. It goes by factors of 10. So it's a log-log natural logarithm scale where we plot those cross sections. And the unit that we use is the barn. If you go to the chart of nuclides and extract cross sections for calculations, you'll find that they're given usually in barns. So in that case, and the X scale is either the electron volt or the million electron volt unit of energy, of kinetic energy of those neutrons in general. Well, we're not just interested in looking at cross sections. We are trying to calculate reaction rates, and we are interested in reaction rate densities, meaning a reaction rate per unit volume. In that case, we need this so that we can calculate, say, fission rates. And if you multiply the fission rate or fissions per second by the energy release per fission, that's 200 million electron volts per fission. So you get million electron volts per second. And in that case, it's a power. And our interest as engineers and physicists here is to calculate power generation and control our nuclear reactors to produce power from it. So in that case, we cannot really go to the lab and carry on an experiment irradiating neutrons, uranium with neutrons. So we are going to carry out what is called in German a Gedanken experiment. This is another way of saying in English a thought experiment. So we are going to take an experiment and try to define the microscopic cross-section in a quantitative way so that we can calculate reaction rate density. So again, we are after the reaction rate density or the number of fissions, say, per unit volume. Density implies per unit volume. So let us take the figure 3 here. And in figure 3, let us assume that we have some material. It doesn't have to be a fissile material like uranium. It could be simply concrete, for instance. And let us take a small thickness of that material. We'll call it the target. The thickness is X, and the cross-sectional area is capital A. So when you take the area of the base of that cylinder multiplied by into the thickness, you get the volume of that little piece of material. And let us assume that I have now a beam of neutrons, directional, so it has a velocity, not a speed, velocity vector, capital V, small v here, impinging on that target that contains a capital N per unit volume nuclei. So in that case, this is the number density or the density of the nuclei in the target material. It could be uranium, it could be wood, it could be concrete, stone, whatever. How do we calculate that capital N or the number of nuclei per unit volume? We use Avogadro's law, as we have used it before. except that we divide the G here in the expression for the mole or gram molecular weight, which is the mass divided into the molecular or atomic weight, divide the G by V, the volume. If we divide by the volume, you get the density. So we use in that case a modified form of Avogadro's law, where G here, the mass, is replaced by the density. And in that case, when we calculate the number of atoms, we don't get the total number of atoms, we get the number of atoms per unit volume. This is Avogadro's number. This is the molecular or atomic weight of the substance in the target. And d rho is the density of the target. So here, the higher, obviously, the number of nuclei in the target, the higher the interaction of the neutrons with the target. And it doesn't depend only on the density of the nuclei in the target, it also depends on the density of the neutrons in the beam itself. So in that case, we denote the intensity, the density or the number of neutrons in the beam by small n, whereas capital N would be for the density of the nuclei in the target. If we take that number of nuclei per centimeter cube and multiply it by the speed or the velocity of the neutrons, we get a number per centimeter cube multiplied into centimeter per second. We get units of number crossing a unit area per unit time. And this is what we are going to call the beam intensity or the current in the beam. Neutrons per centimeter cube multiplied by centimeter per second gives me units of neutrons per centimeter squared per second. It is a descriptive of the number of neutrons crossing a unit area per unit time. So let us have that beam of neutrons here with that density small n interact with the target that has a particle density or nuclei density of capital N. And what we are going to try to do is seek to get an expression for the reaction rate density as a step of basically calculating the power generation from that the neutrons would generate for us in any material. So if you ask ourselves a question, this is now the Gedanken experiment or the thought experiment, what would be the reaction rate? How many interactions between the neutrons and the nuclei is going to happen? And the thought experiment tells us that the higher the n, obviously, the density of the particles in the target, then the higher the reaction rate. The higher the n in the neutron beam, the higher the interaction with the targets in the nuclei in the target. The higher the thickness and the volume in general also, and the speed of the neutrons, the higher the interaction in the target. So we can say that the number of reactions between the neutrons and the nuclei in the target, reactions per unit time, or the reaction rate in that case, is proportional to the area of the target. The higher the area, of course, more reactions will occur. The thickness of the target, the more, the thicker the target, the more reactions will occur. But also the rate would be proportional to capital N, how many nuclei we have in that target. The higher the number of nuclei per unit volume, the higher the reactions per unit time. And definitely also the speed of the neutrons will determine how fast those reactions occur. So we cannot think about any other variable that would affect that reactions per unit time. And this is a proportionality constant. And in mathematical physics in general, when you have a proportionality constant, we can replace it by an equal sign provided we add a proportionality constant. So let us get rid of that proportionality symbol here, replace it with an equal sign, and add a proportionality constant that would be sigma from the Greek alphabet, the small sigma. And then we can write that the reaction rate is going to be that proportionality constant multiplied into the area, multiplied into the thickness of the target, multiplied into the number density of neutrons in the beam, multiplied into the number density of the nuclei in the target, multiplied into the velocity or the speed of the neutrons in the beam. Well, this looks complicated, so let's try to simplify things so that we can gain insight into what's going on in terms of interactions per unit time or the rate of reactions between the neutrons and the material in the target. Let's start with the area A multiplied into the thickness X. That is obviously the volume of the target. So AX here can be simplified by saying that is the volume. And if we substitute the volume here in the equation for the reaction rate and then divide by that volume, we get now a reaction rate per unit volume. So if you take R divide into V, which is AX, we get a reaction rate, reactions per second per unit volume. We call this the reaction rate density. Reaction rate, reactions per second, density because it is per centimeter cube. And the expression becomes simpler. It's now N, the density of the neutrons in the beam, multiplied into the velocity of the neutrons, multiplied into the number density of the nuclei in the target, multiplied into that proportionality constant. And that gives us an interesting way of finding the units of that proportionality constant or give it some physical meaning. So if we take the sigma here, it would be equal to the reaction rate density, that R prime divided into N, V, and capital N. The R prime, we know that it's reactions per centimeter cube per second. We are doing some form of deriving equations using dimensional analysis here. The N here is neutrons per centimeter cube in the beam. The speed of the neutrons or velocity here is centimeter per second, and the number density in the target is capital N nuclei per centimeter cube. You find that centimeter cube cancel, second and second cancel, and we end up with reactions with neutrons also cancel. So we end up with that sigma having units of, centimeter squared. And that is why we call it the cross-section. So that sigma here has units of area, and it represents the effective area that the neutrons are presenting to the neutrons coming from the beam, and that's what we call the cross-section. And in fact, that is what was plotted in the two graphs that we have shown earlier. This is the sigma, the cross-section, and we define the units of the bond as 10 to the minus 24 centimeters squared. It's a very, very small area, but it can be calculated using reactions of neutrons with targets in nuclear research reactors, and obviously also in particle accelerators. So in that case, if we know that sigma here, the cross-section from measurements or from evaluations, like here, these are the group average cross-sections, getting rid of those resonances in the resonance region here, then we are able, in that case, to calculate reaction rate densities. And that is important in the design of shields against radiation, as well as the calculation of the criticality, how to make a nuclear reactor critical in general. Let's go back to the equation here, number 5, which is the equation for the reaction rate density. We had here the density of neutrons in the beam multiplied into the speed of the beam. And this product NV has units of neutrons per centimeter cube for N and centimeter per second for V. So it has units of neutrons per centimeter squared per second. So it has a meaning here. It's a neutrons crossing unit area per unit time. And we like to call beam the current or the beam intensity. So in that case, you find that in the expression for sigma, we can redefine it as being the reaction rate density per unit beam intensity, neutron per centimeter squared per second I, per nuclei per centimeter cube. And again, it checks that it has units of centimeter squared. So by denoting the beam intensity as NV, we can simplify that equation that we wrote earlier. So the reaction rate density now becomes NV, the beam intensity, multiplied into capital N and small sigma. Now sigma has units of centimeter squared, capital N has units of nuclei per centimeter cube. So you find that the product n sigma has units of 1/centimeter or inverse centimeter. And in fact, if you multiply that capital N by the small sigma, you have now a description of how many how much you are summing the areas of all the nuclei centimeter squared per unit volume, centimeter squared per centimeter cube. So we find that the unit here is 1/centimeter, inverse centimeter in that case. So in that case, we have simplified the reaction rate density as being equal to the beam intensity or the current multiplied into n capital sigma. And we can multiply that n capital sigma by together and get what we are going to call the macroscopic cross-section. Before we get there, let us look a little bit deeper at what is that radius of the nucleus and why did we call 10 to the minus 24 centimeters squared the barn. The actual measurements of the radii of atoms in general depend on their volume. So if we talk about the that cross-section, it is not in general equal to the actual area of the nucleus. It is more a description of how the probability of its interaction in different ways with the incoming neutrons at different energies. So if we consider, say, an empirically determined expression for the radius of the nucleus, we'll find that the radius of the nucleus is r multiplied into a constant 1.35 10 to the minus 13 centimeter multiplied into a, the mass number to the 1/3 power. 1/3 power tells us that the radius of the nucleus depends on the mass number. So nuclei like hydrogen would have a very small radius, tiny nuclei, whereas uranium, say the mass number is 235, would be a much higher, larger radius. So if we take the cross-section in that case, just take the cross-sectional area as pi r squared, take that r and square it, you'll find that the actual cross-section of a nucleus is proportional to the mass number to the 2/3 power. 2 because it's squared and 1/3 because it's a volumetric factor in general. So if we take if you take gold, Au is aurum in Latin. So if you take gold, 197, you can calculate the area of the nucleus by taking that A here as 197 to the 2/3 power. You find that the area of the nucleus indeed is in the range that we named the barn. It's about 1.9 10 to minus 24 centimeters squared, which is the barn. And since the cross-section has such a small magnitude, we chose that unit of the barn as being the unit of the cross-sections of the nuclei in general. Incidentally, the characteristic size of an atom is given by what's called the first Bohr's radius, that's designated as alpha sub 0. And in that case, it's 5 10 to minus 10 centimeter, where alpha here is what's called the fine structure constant. You may have seen that into your atomic physics classes. So in that fact, the nuclear to atomic ratio is 2.5 10 to the minus 5. What is the nuclear to atomic ratio? That is the distance of the nuclei's dimension to the atomic, the radius of the atom. And you could see it's 2.5 10 to the minus 5, meaning that we have a factor of maybe 10,000 in terms of the size of the nucleus compared to the size of the atom. So most of the mass of our in nature of the atoms is in the nucleus itself. All right, so we defined that unit that we called the microscopic cross-section, the small sigma, and we said that the interactions with the nuclei can be very different. So we have here a list of possible cross-sections that we take the cross-section for elastic scattering, we take the cross-section for inelastic scattering, we take the cross-section for radiative capture, and we take the cross-section for fission. But there are some other reactions also occur, like a neutron can be absorbed in a nucleus and the proton or a hydrogen nucleus is emitted. We designate this as an NP reaction. A neutron can be absorbed and a triton, an isotope of hydrogen, the heavy isotope of hydrogen, tritium, is emitted. We call this NT reaction. Or a neutron can be absorbed and an alpha particle emitted. We call this N alpha reactions. We group together the sum of the radiative capture where a neutron is absorbed and a gamma photon is emitted when fission occurs, when an NP reaction, NT or N alpha reactions together. All these reactions lead to the disappearance of the neutrons. So when we group those together, we call them the absorption cross-section. And if we sum all the reactions that we have in the list earlier, this means that you take the sigma absorption plus the inelastic scattering and the elastic scattering. That is when we call it the total cross-section. In the textbooks, we also designate what's called the capture cross-section. So the capture cross-section is all the cross-sections here in the equation 12, except for the fission cross-section. So the capture cross-section is the reaction that leads to the disappearance of the nucleus, the sigma absorption minus the fission cross-section. So in general, the absorption cross-section is a fission cross-section plus the capture cross-section. You'll find in the textbooks, they make a terrible error in the calculations or the designations, is that they confuse the absorption cross-section with the capture cross-section. It gives them the same name, and that is not true because the absorption cross-section includes the fission cross-section, whereas the capture cross-section does not include the fission cross-section. In fact, the capture cross-section plus the fission cross-section is the absorption cross-section. So if you carry out the design of a space reactor, if you are with NASA or design efficient reactors, you could make a huge error by confusing the terminology right here. Those cross-sections have been measured by career physicists who carried experiments to provide us with the data that we use in shielding against radiation, using neutrons in nuclear medicine, as well as in the production of power. You'll find that the cross-sections behave differently for different materials. We have seen the one for plutonium-239, but if you look at the neutron interaction cross-section with the light elements, let's take oxygen-16. That's important because we use water, H2O, in moderating those neutrons in existing pressurized water reactors, the PWRs, and the boiling water reactors, the BWR. You'll find that with the light elements like oxygen-16, the reaction does not occur until the energy of the neutron exceeds here, like let's say 4.5 million electron volt. And most of the reactions with say this is the light elements, you find that they're threshold reaction, meaning that you need an energy above that threshold here for those reactions to occur. And that includes not just the NP reaction, the N alpha reaction, the ND, N to N. N to N is a reaction in which a neutron is absorbed and 2 neutrons are emitted. That occurs with very high energy neutrons above 15 million electron volts. Notice this is very different than the cross-section that we have shown earlier for the plutonium, for instance. Depending on the nucleus that is of interest to us, you'll find that the cross-sections have different behavior. You could see here for plutonium-239, an odd-numbered isotope, the cross-section goes up higher, the lower the energy of the neutron. So that's why we moderate the energy of the neutron to achieve a critical configuration. The Chicago Pi #1 used graphite or carbon to reduce the energy of the neutrons, whereas in the whereas here with the heavy, with the light elements, you could see that we have threshold reactions. So they differ for different kind of isotopes and different parts of the periodic table. Let's look at some other reaction interactions here. This is the interaction of neutrons with lead-208. That is an isotope of lead. You could see again, it is a threshold reaction. And something interesting about lead-208 is that it undergoes a neutron multiplication reaction, meaning that the lead-208 absorbs a neutron and emits 2 neutrons. For neutrons that are in the range of, say, 7 or 8, this is 7 from 7 to 8 million electron volt, you are multiplying the number of neutrons in lead. And you can even get an N3N reaction with neutrons within the range, say, of 15 million electron volts. So fusion neutrons in lead can multiply the number of neutrons. Hence, it has an application in fusion reactors. For that, in that case, we need to multiply the number of neutrons to have enough neutrons to produce tritium for the DT or deuterium-tritium fusion reaction. So lead in that case would be considered as a neutron multipliers, but only if we use high energy neutrons. So those properties, of course, are used in the design of different configurations. If we looked at plutonium, well, we have to look also at uranium-235. 235 is a fissile isotope in uranium, and it displays the same behavior as plutonium-239, but the resonance here at low energy is not as prominent as in plutonium-239. That's why I showed the 239, so that I can show you the existence of that resonance here. So at that particular energy here, the neutrons are absorbed like basically you can detect radio waves in a tuning or circuit, RLC, resistance, inductance, capacitance circuit, a tuning circuit. In uranium-238, let's compare the numbers here. When you take uranium-235, look here at the cross-section for fission at very low energies. Neutrons here, that would be 1 electron volt, that would be 0.1 electron volt, and when we deal with thermal neutrons, it's 0.025. So in that region right here, you find that the fission cross-section would be in the range of 1,000 bonds. But look at the cross-section for uranium-238. And if you read the cross-section for uranium-238, at low energy, it's only 10 to the first power 10 bonds. So look here, you multiply the value of the probability of causing fission by a factor of 100, 2 orders of magnitude if you use uranium-235 compared to uranium-238. All right, so this is the actual cross-section for uranium-238. 2 important reactions that happen also in the applications of nuclear reactor designs is when we are going to be building in the future fusion reactors. And in fusion reactors, we'll be trying to use the 2 isotopes of hydrogen, deuterium, and tritium. So in that case, you'll find that we use the isotope lithium-6. A neutron interacting with lithium-6 gives us a triton. And in that case, you could see here that cross-section for producing a tritium nucleus by the interaction of the neutron with the isotope of lithium-6. And you could see it's a thermal reaction. Again, it's 1,000 bonds when the energy of the neutrons are very low. However, lithium in nature occurs primarily as lithium-7. So you could see the reaction for lithium-7 is in fact a threshold reaction. So it happens only with high energy neutrons. So high energy neutrons can produce tritium for us, but we'll have to basically depend on lithium-6 to produce those neutrons in general. In the same way as lead, uranium-238 can be a neutron multiplier. So you can see here an end-to-end reaction or an n prime T reaction happens as a threshold when we have energies in the range of the 10 million electron volt, like the fusion neutrons, the DT reaction. When we calculated its Q value, we discovered that the neutrons have an energy of 14.06 million electron volt. So the study of those cross sections are important in the sense that different properties can be used to produce different designs and different effects, whether it's fission or fusion. It's very important in the equation that we wrote for the reaction rate density to calculate the number density of nuclei in any, not just single substance, like if you deal with calcium, for instance, or sodium. Sodium is used as a coolant in fast reactors. In that case, we are interested not in the original form of Avogadro's law, taking the mass divided into the molecular or atomic weight multiplied into Avogadro's number, but we are interested in the atoms or nuclei per centimeter cube. So we divide the G by V, the volume, and G divided into the volume, mass divided into volume is the density. So the simple equation to consider for calculating number densities is basically the modified form of Avogadro's law that we are given here. The question and the difficulty comes out when we deal with not substances, pure substances, like say calcium or lead, but when we deal with different isotopes or when we deal with compounds like H2Os. Luckily for us, the cross-sections for compounds add up. For instance, the cross-section for water, H2O, is the sum of the cross-section for the hydrogen as well, H2, as well as the oxygen, O. This is the only place in the literature where you'll find really a description on how to calculate number densities for different compounds. It's not in the textbooks whatsoever, so I went through the trouble of figuring it out right here. So if you have a single species like sodium, sodium is used as a coolant for fast reactors, and you want to calculate the number density, you go to the chart of the nuclides or Wikipedia or the handbook of physics and chemistry, and you get the density for sodium. You don't need the just to use 1 gram or 2 grams, you use just the density. So if you get the density of sodium and substitute in our modified form of Avogadro's law, you'll find that you have 0.02 10 to the 24th atoms per centimeter cubed of sodium. And you can use this now in the equation that we derived for the reaction rate density. It was equal to the beam intensity multiplied into the capital N, the number density of the nuclei in the target, multiplied into the speed, the intensity of the beam multiplied into the cross-section multiplied by that capital N. So we need to calculate that capital N in the design when using different substances. What about if you have a molecular or an isotopic composition? In that case, the rule of thumb is that you have to calculate use the calculations in atomic percent. When we write A/0 here, that is atomic percent. Percent comes from the French pair by cent, S-E-N-T, 1 cent is 1/100th of a dollar in that case, but is 1/100th. When you write V/O, that's volume percent. When you write W/O, that's weight percent. Here we are talking with atomic percent. So all you do is take the density of the mixture and modify it by the constituents, and the cross sections add up. For instance, if you have an element, the number density of a given element is the density of the mixture divided into the atomic or molecular weight of the mixture. If you have a molecular composition, let's take the example of water. The density of water is 1. The mass, molecular weight of water in that case is 2 atoms of hydrogen, 2 multiplied by 1,000 atomic mass unit, and plus the mass of the oxygen, which is 1 atom of oxygen. The atomic weight is 15.99. So the mass of the mixture is 18. And all you do now is take the density of the mixture, the density of the water here, multiplied into the 0.6 O2 10 to the 24. This is Avogadro's number. And you notice why previously, when we describe Avogadro's number, we didn't write it as 6 10 to the 23rd power, like in different other sources, textbooks or books or reports. We used 0.6 because at 10 to the 24th plus 24 will cancel later on when you multiply that capital N into the cross section, which is 10 to the minus 24. So they cancel out, and we write Avogadro's number as 0.6 10 to the 24th power. The molecular weight of water is obviously 18. So in that case, the number density of water, molecules of water, molecules per centimeter cube is 0.03 10 to the 24th power. And of course, in water, H2O, we have 1 atom per oxygen per atom of water. So this is the same as the number density of water. But if you think about H2O, you have 2 atoms of hydrogen per atom of water. So in that case, you take the number density of water, multiplied it into 2 to get the number density of the hydrogen. And the interesting thing, of course, is that oxygen has a different cross sections than hydrogen. But when you calculate the microscopic cross section, as we tried to describe the product of N into the microscopic cross section, you'll find that you do it for both of them and then add them together. It also applies to isotopic compositions, like if you are dealing with boron. Boron is used in the control rods to absorb neutrons in nuclear reactors, but it's also used in neutron cancer therapy to kill soft tissue tumors, say in the brain. So you use the isotope boron 10, preferentially to the boron 11 isotope in boron. So the mixture of boron, the 2 isotopes, is 2.45 grams per centimeter cube. So all you have to do is modify the density of the isotope here, depending on its atomic density. You take 2.45 multiplied by the atomic percentage of boron 10.18, and for the number density of boron 11, you multiply by 8.82, which is 80%. So all you have to do is simply use logic to calculate an effective density of the in the isotopic mixture. You can do this also for mixed molecules like boron carbide. Boron carbide is a shielding element because of it contains that boron, and boron absorbs neutrons, and carbon slows down the neutrons through interactions with the carbon nuclei. You can also deal with compositions by weight. You can deal with alloys, and if you have enrichment. Notice here now it's not atomic percentage that is used by the weight percentage. So for instance, in uranium-235, when we talk about the enrichment in the chart of the nuclides in atomic percentage, but when we deal with enrichment is 20 weight percentage. So you modify the density of each isotope. So if you take the density of uranium, mixture of uranium-235 and uranium-238 at 19.1 gram per centimeter cube, and you want to calculate the number density of uranium-235, you take the density of the mixture modified by the proportion in gram per, the proportion in weight percent of uranium-235 in it. So that would be fuel that contains really 20% enriched uranium. Remember our previous chapter on enrichment. 20% enrichment in the uranium-235 isotopes is, according to the Non-Proliferation Treaty, allowed for research reactors to produce really neutrons for medical applications and for transmutations of the different radioactive isotopes. If you exceed the 20%, you would be abrogating the Non-Proliferation Treaty, because now you would be producing uranium as fuel for nuclear devices. So in that case, you multiply the enrichment in weight percent into the density of the uranium that you are using, and then use the modified or effective density to calculate the number density in atoms per centimeter cube of uranium-235 and of uranium-238. So the uranium-235 would be 20%, and uranium-238 would be 80%. The same applies to alloy compositions. For instance, zirc alloy 4, that is an alloy of zirconium. Zirconium has interesting properties in nuclear reactors. It is used for the cladding or the can that contains uranium dioxide fuel. And the zirconium has two interesting properties. It resists corrosion by water. Obviously, you don't want your fuel elements to corrode in a nuclear reactor. And in addition, it has a very low absorption cross-section for the neutrons. And you want to preserve the number of neutrons you have because they are what causes the fission process. So zirc alloy has a density of 6.74 gram per centimeter cube, and an alloy of zirconium, in that case, it contains 0.1% chromium, 0.21% iron, and 1.4% tin is used in nuclear reactors. So what you do, you take that density 6.745 multiplied in the weight percentage of each one of the isotopes, and you can calculate the number density of each one of the isotopes. You can apply this also to aqueous solutions if you have, for instance, sulfuric acid in water, and I'll leave it for archival purposes here. If you need to use it in design calculations, you'll find the source for how to do it here. You can also have heterogeneous systems that are not weight percentage like alloys or enrichment, but if you have a volumetric mixtures like by volume. So in that case, you have the volume percent rather than the weight percent or the atomic percent. Again, you use the logic in estimating the number densities. When we deal with nuclear reactors, to simplify calculations, we homogenize the materials. Like if you have uranium dioxide and spacers in the reactor made out of iron, so you calculate the cross-section of each one of them, and they add up linearly to calculate the cross-sections for some given mixture or alloying element. Let's take an example. If you take the uranium dioxide fuel, it's a ceramic, its density is 10.5 gram per centimeter cube. Remember, uranium has a density of about 18.9 gram per centimeter cube. But let's say that that uranium has its uranium enriched to the 30% weight percent in the uranium-235 isotope. So if you want to calculate the number density of uranium-235, we take the effective density of uranium-235 and multiply it into Avogadro's number and divide into the molecular weight. How to calculate that effective density? You take the density of the uranium dioxide here, UO2, multiply by the mass of uranium in uranium dioxide, multiply it into the enrichment here, which is 30%. And in that case, you get the mass of the mass of the number of atoms of uranium, and then you multiply by the ratio of uranium-235 into the uranium mixture, and you get an effective mass for uranium-237. I should add here atomic mass unit, and you can also calculate the molecular mass of the uranium dioxide, and you go on and you are able to calculate the number density of uranium-235. Well, we said it already, is that the microscopic cross-section is multiplied in the equation for the reaction rate density by the number density of the element. And that's why we went through the trouble of how to calculate that capital N here, given whether we have a single a material like sodium or a composite material like water, H2O, or alloying elements, or volumetric or mass mixtures like enrichment. So the taking that number density, which is really number per centimeter cube, and multiplying it by the sigma, which is the area of the nucleus. So here it has a physical meaning. The physical meaning is that it is an area per unit volume. So in that case, that product N, capital N sigma, is a summation of all the microscopic cross sections of each one of those nuclei in our target, in our Gedanken experiment, per unit volume. So it's a whole summation of the areas of the nuclei per unit volume. And it has units of 1/centimeter or centimeter minus 1. So if you have a mixture of different species of material, you take the first material N1, multiply it into sigma 1, it's microscopic cross-section, and you sum it over all the species, and that's what we call the total macroscopic cross-section. So the small sigma here is a microscopic cross-section, a property of one atom. When you multiply it by the number of atoms per centimeter cube, it is macroscopic. Macroscopic is a summation of all of them over the nuclei. That sigma has also another interesting physical meaning. If you take 1/sigma, it has units now of centimeter. So the 1/sigma has a unit of centimeter. And in that case, it has the meaning of a mean free pass of the nuclei. So in that case, the inverse of capital sigma has the physical meaning of the inverse mean free pass. Mean free pass is a distance traveled by the nuclei between two interactions in the medium. So lambda here is described as 1/sigma. And we come back to our reaction rate density, and we find that we can write a very simple equation for it, that the number of reactions per centimeter cube per second is nothing than that macroscopic cross-section, which is the microscopic cross-section from the files, for instance, the ENDF file. This is the evaluated nuclear data file, or from the table of the nuclides, and you multiply it by the beam intensity or the current in neutrons per centimeter squared per second. And this is a very simple reaction. If you know the capital sigma and you know the beam intensity, then you can calculate, say, the number of fissions per centimeter cube per second, or the reaction rate per second density, reaction rate density. The problem with that I here is that in our Gedanken experiment, we assume that it is directional, meaning that it's a beam of neutrons coming from a particle accelerator or from a nuclear reactor. When in fact in a nuclear reactor, the neutrons do not have directional properties. They are moving in all directions. So in that case, we cannot use that equation as it is. We have to relax it a little bit by saying that the number of neutrons crossing a unit area per unit time is more like a scalar quantity. We'll call it phi, which is equal to n, but the magnitude of the velocity, no beam exists there, and that nv now still has the units of the beam intensity or the current of neutrons, and we call that quantity the neutron flux. It is still units of neutrons per centimeter squared per second, and when we take now the neutron flux and multiply it by the macroscopic cross-section, we get the reaction rate density. So this equation applies to particle accelerators or beams of neutrons. We relax that for a nuclear reactor by defining the neutron flux. We'll see later that the neutron flux doesn't have directional properties, so it's a scalar quantity, same as temperature. It's a scalar quantity. You cannot say that temperature has a vector, or maybe the hydraulic head doesn't have a directional properties. In electrical engineering, the voltage cannot be a vector. It's like temperature, voltage, hydraulic head, and neutron flux are all scalar quantities. We'll take that into account later on in our calculation. So the reaction rate density then in a nuclear reactor is really the macroscopic cross-section multiplied into the neutron flux. And when you substitute the macroscopic cross-section here for fission, you don't get the reaction per centimeter cube per second, you get the fissions per centimeter cube per second. And if you want to calculate the power, you multiply by the energy release per fission event, 200 million electron volts per reaction. So it becomes million electron volts per centimeter cube per second. And this is the power density or the power per unit volume. And that's why this equation here that we simplified is extremely important in the design of nuclear reactors. If you want the total reaction rate, obviously you come back by multiplying into V. So multiply into V in centimeter cube, you get the total reaction rate. So this is a simplified way of describing how the reaction rate density can be calculated and how the reaction rate can be calculated. In essence, though, we can now generalize our equation. We took here a special case where we have a flux that is uniform all over the reactor. But the flux, in fact, differs from one point of the nuclear reactor to another. So the flux is a function of the position in the reactor. Near the center, you'll find that we have more reactions occurring than near the periphery of the reactor. And the flux also depends on the energy of the neutrons. The same for the macroscopic cross-section. It depends on the position of the reactor, whether it's in the fuel or in the moderator, and it's also a function of energy. So in fact, for realistic calculations, we have to generalize our equation here for the reaction rate in a nuclear reactor as an integral over the energy, E, and integral over the volume, R, of the whole reactor, and dE dV, where the flux is a function of position and energy, and the macroscopic cross-section is a function of position and energy. And basically, we break that double integral and generalize the equation into summations over different regions of the reactor where we have different fluxes and different energies. And basically, you replace the two integrals by a summation sign over elements of volume, delta V's, and elements of energy, delta E. And that's how you calculate the reaction rate over a nuclear reactor. If you have had classes in quantum mechanics, this description here, the general description of the reaction rate, can take the inner product format. So this is the inner product here using quantum mechanics or wave mechanics. You multiply that into the volume, but it's really the inner product of the flux as a function of energy into the macroscopic cross-section as a function of energy. All right, so this is now getting into the design of nuclear reactors. We need to calculate the reaction rates so that we can calculate the power distributions. The neutrons, though, as they're thermalized, follow a Maxwellian distribution. The Maxwell-Boltzmann distribution describes in the room that we are sitting in, either myself or yourselves, the energy of the molecules in the room. And it can be described, the Maxwellian distribution in thermodynamics, either as a function of the velocity of the molecules of gas. It could be also an internal combustion engine, or in a nuclear reactor, in our case, it follows a Maxwellian distribution. The Maxwellian distribution can be described either as a function of the velocity of the particles or as a function of the energy of the particles. Let's take the case of the velocity of the particles. So obviously, neutrons in a nuclear reactor behave according to the Maxwellian in terms of their interaction with the moderator, and the Maxwellian distribution as a function of speed of the molecules, or in our case, the neutrons, has that form here. It has a negative exponential, half mv squared, the kinetic energy divided into kT, which is the thermal temperature, kT, that has units of energy, in fact. And then you have a factor of V squared here, and a factor where you have the temperature in kelvins in the moderator itself. This distribution is a probability density function because it can be normalized into the total N of molecules of neutrons in the medium that we are looking at. And when we use a lot of thermodynamics, T here is usually the Kelvin temperature. Remember, that's 273 plus degrees Celsius. You cannot go use degrees Celsius like in the first test. Some people made that mistake, and it was pointed out to them. You can rewrite that Maxwellian in a simple way. If you take that factor, capital C here, you'll find that you have a V squared e to the minus V squared as the distribution. The Maxwellian distribution governs basically neutrons that are in thermal equilibrium, when they have been moderated in the medium. And the moderator in that case, in thermal equilibrium with the neutrons, would be the graphite in the Chicago pile #1, or in high temperature gas-cooled reactors, or it could be the water in light water reactors, the boiling water reactor, or the pressurized water reactor. And in that case, if it's neutrons have a Maxwellian distribution, then we can estimate their most probable velocity. So what is the most probable velocity? The most probable velocity is the velocity of the neutrons when they are at the peak of the distribution, where the slope at the peak of the distribution is 0. So to determine the most probable velocity of the neutrons in a Maxwellian distribution or a reactor operating at a given temperature capital T, you take the derivative of the Maxwellian dNV by dV and equate it to 0, and then solve for the speed in that case. And you find that the most probable speed, V most probable, is the square root of twice kT over m. And then you can calculate from that most probable velocity, you can calculate what is the most probable energy, which is half m V most probable squared. Oh, look what we get here. We get the kT. That's what we call the kT newtons. So when we say that 0.025 electron volt neutrons in thermal equilibrium with the medium as the most probable energy, you'll find that it is really the energy, the most probable energy is kT. So it's thermal neutrons, or neutrons in thermal equilibrium, according to the Maxwellian distribution in nuclear reactors, are called the kT neutrons. And it's interesting to note that the thermal neutron energy is independent of the mass. See, there is no m here in the expression. The most probable energy is different from the average neutron kinetic energy, which is equal to 3½ kT, because half kT is each degree of freedom. And we can calculate the average energy of the neutron, and we can get that it is not kT, but it's 3½ kT in thermodynamics. The most probable velocity in that case, if we take the kT, take the Boltzmann constant multiplied into T, the temperature at 293 Kelvin, which is 273 plus degrees Celsius, turn your electron volt into ergs, you'll find that the most probable energy is 0.025 electron volts. And that brings us back all the way to the first chapter in our course, when we said that the graphite acted as a moderator in the Chicago pile #1. The water, or the heavy water, act now as moderators in the light water reactors or the heavy water reactors that we operate today. The most probable velocity for neutrons at room temperature, or 20 degrees Celsius, can also be calculated for that expression that we get for the most probable velocity, and this is 2200 meters per second. So when you go to the chart of the nuclides and you get the cross section, say for uranium or water or sodium or beryllium, they are also listed under the cross sections for 2200 meter per second neutrons, meaning that really they are for neutrons in thermal equilibrium in the moderating medium. So neutrons in thermal equilibrium, or kT neutrons, according to the Maxwell-Boltzmann distribution, are referred to as the 2200 meters per second neutrons. If you go to the chart of the nuclides, that's how they are listed there. If we want to talk about not just the most probable energy or velocity of the neutrons, we can talk also about the mean or the average or the mathematical expectation of the neutron velocity. In that case, we take the Maxwell-Boltzmann distribution, N of VdV, and to calculate the average energy, we multiply this distribution by V. This is statistics or probability theory, and we get in that case the mean value, or the mathematical expectation, or the average, whichever context we are talking. Statisticians, mathematicians, and physicists give it different names, but it's all the mean, average, or mathematical expectation. And if you carry out, multiply the Maxwell-Boltzmann distribution by V and carry out the integration, a complex process where you have to integrate by parts, you find that the average energy of the neutron is not the kT, but the square root of 8 kT over pi m. So in that case, when you operate nuclear reactors, we obviously do not operate them at room temperatures. The light water reactor, for instance, operate at a temperature of about 350 degrees Celsius. So in that case, you could see that the speed of the neutrons, and that's also where the flux is calculated, depends on the temperature at which we are operating the nuclear reactor. So when we get the cross sections at room temperature, the 2200 meters per second cross sections, we need to introduce a correction factor that corrects for the temperature at which we are operating the reactor. So if you estimate the cross section at room temperature, sigma sub A 293, you'll find that you need to correct it by T to the 1/2 power the room temperature, 293 to the 1/2 power, divided by the temperature at which you are operating your reactor. Like that would be 273 plus 350, maybe for light water reactors. And in that case, all the absorption cross-section that we use at a given temperature at which we are operating the reactor are corrected by that factor of 293 divided into T, the operational temperature of the reactor. There's another correction that is introduced in terms of the Maxwellian distribution, and where we take the the mean velocity, the square root of 8 kT over pi m, and divided by the most probable velocity, or the maximum, the velocity at the maximum of the Maxwellian distribution, that is the square root of twice kT over m, the pi, and the m and the m cancel, the k and the k cancel, the t and the t cancel, and we end up with another correction factor, which is 2 over the square root of pi. It's square root of 4 divided into pi, which is 2 over the square root of pi. So whenever we are using cross sections in general that we get from the tables provided to us, we need to introduce two corrections: a correction because we are using a Maxwellian, and a correction because we are operating the system at a given temperature other than 293, which is 273 plus 20, the room temperature. For instance, we take gold. The gold has two isotopes, 197 and 198. And notice here the very different cross sections in bond. B is the unit of bonds. The 198 absorbs neutrons very readily. It has a cross section of 26,000 bonds, whereas the other isotope of gold, 197, has only about 100 bonds. So you can, in fact, use gold foils to measure the flux in a nuclear reactors, the power level. You introduce a gold foil, a little tiny piece of gold, and irradiate it with the neutrons. That produces the gold 198, which is a very high neutron absorber. But when you calculate the cross section for absorption here, you take that number and you have to modify it by the Maxwellian correction, the root square of pi over 2, and the temperature correction, 293 is the room temperature, but here you are operating it at, say, 50 degrees Celsius in a nuclear reactor, so you find that you get a big difference. Instead of getting the absorption cross-section as 98.8 bonds, in fact, at this higher temperature, it is only 83.3 bonds, so that's almost 10% difference. And the absorption cross-section, instead of being in the range of 26,000 bonds for the gold 198, when you apply the Maxwellian correction and the temperature correction, you end up with 21,000 bonds instead of the 26,000 bonds as the absorption cross-section. So in calculations of nuclear reactors, we take this into account. And that is a description of how neutrons' interactions with matter are in general considered. By defining the neutron flux and knowing the number of densities, we can calculate reaction rates. I'll stop the sharing here and look at the chat room if there are any questions. If there are no questions, we'll continue and see if we can cover another chapter. Okay, we measure the cross section so that we can calculate reaction rate densities, but eventually we'd like to see how those neutrons interact with materials. And when they interact with materials, we are interested in two situations. One situation is when we have non-multiplying media, meaning there is no fissioning of the uranium. The terminology multiplying media comes from biology, because we mentioned earlier that neutrons behave almost like bacteria, and that they fission, bacteria fission, and they also fuse, fusion. The same equations, interestingly, apply to both neutrons and the bacteria. The process of describing how neutrons interact with matter can be described by what's called transport theory, but we are going to deal today with an approximation of transport theory, which is described as neutron diffusion theory. And it is true for neutrons when they are thermalized or in thermal equilibrium with the medium, that they basically diffuse in the same way that, say, if you drop a grain of salt or a grain of sugar in water, it basically has a high concentration, and that high concentration diffuses the sugar or the salt in the water. And that process of diffusion is described in physical chemistry by what's called Fick's law. So the neutrons, in fact, in a nuclear reactor behave as they diffuse according to Fick's law. So diffusion theory is used in the design of existing nuclear power plants when you have a good moderator that is being used. If you are doing, you don't have a good moderator, then you have to go back to what's called transport theory. I have a chapter there. You can read about it in more detail. When you use diffusion theory, we use what's called the transport cross-section. The transport cross-section is basically a description of how is it that a neutron scattering away from a nucleus diffuses away directionally away from the nucleus. So in fact, you'll find that the cross-section or the mean free path is not just lambda sub s, but it's also the mean free path projection according to the angle of scattering on the same line. So if it scatters twice with the cosine of the scattering angle, cosine theta 1 being designated as mu average, you'll find that the total difference or the transport of the neutron from this point to another point is the sum of the initial distance traveled, z sub 0, plus the projections after one scattering, two scattering, and n scatterings in general. This is what we call the transport cross-section, and it's a correction to the diffusion theory cross-section in general. Coming back to diffusion. Diffusion in general in physical chemistry is described by Fick's law, and that's something you can carry as an experiment yourself. Just drop some salt or some sugar in water, you'll find that it diffuses. And Fick's law in chemistry or physical chemistry says that if the concentration of a solute in one region is greater than in another of a solution, the solute diffuses from the region of higher concentration to the region of lower concentration. Very simple statement and observation that you can all make. Just drop a drop of a coloring agent in water. It's a high concentration. You'll find that it diffuses from the region of high concentration to the region of low concentration. And in that case, we can describe that mathematically by talking about the gradient or the slope that describes how high the concentration is in one point of the medium to another. And in fact, neutrons behave like a grain of salt dropped in water. Near the center of the reactor, we find that the neutrons are concentrated. So they peak near the center of the reactor. So they are not really crossing a unit area per unit time, or the flux is not the same in all parts of a nuclear reactor. You'll find that near the periphery, because they're leaking, their concentration is lower. So the distribution of the power in a nuclear reactor, how we produce the steam, is higher near the center of the reactor, but it's also how we are burning the fuel and how we have to replace the fuel near the center of the reactor. So the distribution as a function of space of the reaction rate in a nuclear reactor is of great importance, and it follows that Fick's law. So it is imperative for us to describe the mathematical description of Fick's law. And if we take a very simple description, we can say that a current forms in a nuclear reactor without going through that whole theory here, and that a current is formed that is basically proportional to the negative of the gradient of the neutrons in the nuclear reactor. So that would be a diffusion coefficient, like in Fick's law, and gradient is a gradient operator that you have learned about in your calculus classes. The gradient is a vectorial quantity. It's d by dx, what we called the flux earlier in the x direction, and d partial by dy, the flux by dy in the y direction, plus the d by d phi by dz of the neutron flux, which is, remember, the neutron flux is a number of neutrons crossing unit area per unit time in the z direction right there. So this is a vectorial quantity. You see here the x vector, y vector, and z vector. And we call this a gradient because it shows the slope of how the neutrons are really, how speak they are near the center of my reactor. And that 1/3 the macroscopic scattering cross-section to the total square macroscopic cross-section is really what is called in chemistry the diffusion coefficient. But for neutrons, it has to do with the number densities and the microscopic scattering and the total cross-section. That gradient operator in your calculus classes has been written as the grad phi. Grad phi is simply that partial derivative in the x direction, in the y direction, and the z direction. Notice that the gradient operator always acts on a scalar quantity. So our flux here doesn't have vectorial properties. It is a scalar. And as I suggested earlier, similar quantities would be the temperature. It's a scalar quantity, but the gradient of the temperature is a vector, right? So when you take the gradient of, you always take the gradient only of a scalar quantity. The gradient of the temperature gives us Fourier law of conduction. The gradient of the voltage tells us what is the electric field. So when you take the gradient of scalar quantity, let's be more general here. Let's talk flux, temperature, hydraulic head, or voltage. You always take the gradient of a scalar. Oh, but it gives you a vector. So according to Fick's law, we have a current now, a vectorial quantity that is minus d, the gradient of the flux. The phi itself is scalar, but when you take its gradient, it becomes a vector, and this is what we call the neutron current, and it's a minus sign here because the slope is decreasing in the negative x direction. So it tells us basically that the current density vector is proportional to the negative gradient of that neutron flux that we defined in the previous chapter. And it establishes a relationship between them under the assumptions of, say, we have isotropic scattering in all directions of the neutrons, so they don't have a preferential direction. That is not the case. That is the case for thermal neutrons, but it's not the case for high energy neutrons, like the ones from the DT reaction coming from fusion. They have anisotropic scattering, and diffusion theory would fail in doing calculations. We need to use a more advanced transport theory that takes the directional property of the diffusion of neutrons. Diffusion theory basically does not apply close to boundaries. It doesn't apply when you're close to sinks or sources, like very close to the fuel, or if you have anisotropic scattering, meaning that the probability of scattering in any direction is not the same. And it also does not apply in highly absorbing medium. In that case, we have to go to the more advanced transport theory. However, it is very useful for the design of our existing nuclear reactors and shields against neutrons of low energy. And in that case, we are going to use it to describe or derive an equation for the diffusion of neutrons in general. Remember, we are going to use the concept of the flux, which we said is a scalar quantity. And that scalar quantity is the number density of our neutrons multiplied into the speed, and not the velocity, it's the speed. So that's a scalar quantity. Again, think about temperature, hydraulic head, and voltage. All of these are scalar quantities. When we take their gradient, they become all directional or vectorial quantities. Let us take the very elemental control volume that we used in other classes when we dealt with hydraulic systems or electromagnetic systems or temperature systems. We take any control volume because it's arbitrary. It can take any shape. It could be a cube, it could be a cylinder, it could be a parallelopiped, or any volume in general. And to derive an equation for the behavior of neutrons, like in, again, electromagnetics or thermodynamics, we take a balance equation. So we take that volume, and over that volume, we describe the rate of change as a function of time of the neutrons in that volume V. It is obviously going to be to the production rate, how many neutrons we are producing in that volume from fission, obviously, minus the neutrons that are absorbed in that volume. And if you're going to consider a given volume, it has a surface, and that surface would be leaking neutrons. So when you take the production minus the absorption minus the leakage, that is the time rate of change of the number of neutrons in that volume. This is a qualitative description. Let's turn this into a mathematical description. So we write here for the time rate of change as d by dt, an integral over the volume of the number density of the neutrons in that volume integrated over the volume. The production rate is going to be the source of neutrons. So we write here for the first term here, an integral of the source of neutrons as a function of position and as a function of time. The absorption term is definitely the absorption rate. And we said that the absorption rate is going to be the flux phi as a function of space and time multiplied into the macroscopic absorption cross-section and integrated over the volume. The last term in the balance equation is leakage from the surface. And when we consider the leakage of the surface, we take the current at the surface normal to the surface. So we take a dot product with a small tiny vector here perpendicular to the surface and integrate over the surface. And that surface integral here from what's called the Gauss's theorem or from calculus again is an integral over the surface. So it's very inconvenient for us to use 3 volume integrals earlier in the balance equation and then have a surface integral. But Gauss's theorem or Green's formula comes to our help. It tells us that surface integral can be equated to the divergence of the current. So this is now not the gradient operator, but this is the divergence operator, which is d by dx, the j sub x component of the current, plus d by dy partial, the y component of the current, plus d by dz partial, the z component of the current. And the interesting thing is that the gradient operator always acts on phi, for instance, as a scalar and gives us a vector. But the divergence operator, as you could see here, always acts on a vector. And guess what? It gives us a scalar. So, but the Gauss's theorem allows us to turn that volume integral, that surface integral here of the leakage of neutrons from the surface into a volume integral. So in the equation of the balance, we have now 4 terms that are all integrals over the volume, so that we can join them all together under a single integral of the volume, and you end up with the rate of change of the flux minus, if you bring this to the left side, minus the source term, plus the absorption rate. The minus leakage here becomes a positive sign. All integrated of the volume are equal to 0. But we said that the volume is arbitrary, so it doesn't matter really what kind of a volume, what shape of a volume I have. So in that case, the content of the volume integral are equal to 0, and that's what we call the diffusion equation. Now, remember that we also invoked for diffusion theory Fick's law. And in Fick's law, the current was described as minus the gradient of the flux. So, and it becomes here the divergence of the current. The current is minus, so the minus and the minus become plus. But remember that this is leakage from the surface. So even though it has a plus sign, but in fact, it is a loss term from the number of neutrons from the surface, minus the absorption rate of the flux, plus the source is equal to the rate of change of the flux as a function of time. So this is the general equation in terms of the flux that governs the behavior of neutrons when they diffuse in a medium. And it applies to nuclear reactors. When you have fissile material, the neutrons are multiplying, as well as, say, shields, where the material of the shield is not multiplying. Solving the equation as it is here is extremely complex. So we need to simplify it, so that we can gain insight into realistic system. We do that in all branches of science or engineering. So let's first make the first simplification. Notice that this is a partial differential equation in space R as well as in time. So it shows the behavior of the neutron flux, which is the number of neutrons crossing unit area per unit time, and as a function of space, the vector R, and the function of time. Some gentleman by the name of Helmholtz derived a simple form of that equation that applied in electrical engineering to basically the design of transmission lines, how electricity moves in transmission lines. And this gentleman is named Helmholtz. And what he did is that he simply assumed first that D here, the diffusion coefficient, is a constant, it's not a function of R. So we take, in that case, a homogeneous medium. So if you take this D out as a constant, you end up with the divergence operator acting on the gradient operator. And when you do this, the divergence of the gradient, you end up with what's called the Laplacian. Notice that the divergence operates on vectors. So these are the components of the vector, which is the gradient. So in that case, we end up with a simpler equation with D is a constant for a homogeneous medium. And basically, we know the divergence of the gradients is the del squared, or the nabla, or the Laplacian operator. The Laplacian operator allows us to solve for the criticality of nuclear reactors or design shields against neutron radiation in different configurations. So if you deal with the Cartesian coordinates, that Laplacian takes the shape of d partial square by dx squared plus d square partial by dy squared plus d square partial by dz squared. So it's a partial differential equation that we get there. In cylindrical geometry, the Laplacian operator takes form 1 over r d partial by dr, r d by dr. And you have also a component in the cylindrical angle as well as in the z direction. So you think about the cylinder in that case. In spherical geometry, it's different than for Cartesian geometry or cylindrical geometry. And these are the 3 geometries that we meet really in the design of nuclear plant reactors or any kind of configurations. We don't get maybe in spherical like a hemisphere. It's very difficult to deal with the math there, but The del square in spherical geometry is 1 over r squared d partial by dr, r squared d by dr. And then you have the polar angle, theta, coming into parts of the Laplacian. And you have also the azimuthal angle phi in the geometry. So we have angular variables in the z direction, is z and z here, and the cylindrical angle here, the polar angle, as well as the azimuthal angle. If you have full cylinders, then that term and that term cancels out. This one can remain in a finite cylinder. For spherical geometry, that polar angle and the azimuthal angle simply terms disappear. So we are going to start by using the cylindrical geometry then in solving for the power distributions in nuclear reactors, and then look at the Cartesian and the cylindrical geometry. So spherical geometry is the simplest in that case. If you're writing computer code or computer program, the Laplacian takes basically a general form, 1 over r to the alpha power d by dr, r to the alpha power d by dr, where alpha takes a value of 0 for Cartesian coordinates, 1 for cylindrical coordinates, and 2 for the spherical coordinates. Now, where is the contribution of Mr. Helmholtz? Mr. Helmholtz suggested, oh, okay, we need to solve that equation without the time dependence. So we take the equation for neutron transport here at steady state. So that d by dt term here is assumed to be 0. Now, definitely, the behavior of the flux or the voltage in a circuit depends on time, but the time behavior usually is a transient. When you turn on a switch, that time dependence appear in the voltage and current that you get to start on, say, the light in your room. But at steady state, only those terms apply. So in that case, if we take out the time dependence, we end up with a very simple equation, and that is what we call the Helmholtz equation. And this is the equation that governs the behavior of neutron in any medium. So look at the simplification here. The time dependence is not there anymore. It's only a space dependence. The del square operator is d square by dx square partial, d square by dy square partial, plus d square by d z square partial. All right, so it's a simple equation. We can even simplify it even more and give it a physical meaning by dividing into that diffusion coefficient, which has units of centimeter or meter. So if you divide into d, you end up with S dividing into d on the right-hand side. And then you have sigma A, the macroscopic absorption cross-section, divided into d. And that has a physical meaning, 1 over L squared, or 1 over d over sigma A, has units of the square of a length. And that's why we call that L, which is the square root of d over sigma A, we call it the diffusion length. The meaning here is not like the mean free path, which is the distance between, say, a scattering and an absorption, or a scattering or another scattering. This is the average distance traveled by the neutron from the time it is born from fission to the time where it leaks from the surface, our minus d del square phi appears here, or through absorptions in the medium. So we have another physical meaning for the terms of the equation. And that equation here is some equation that you have seen in different other applications. A Laplacian equation, the equation of Laplace. Think about the flux here replaced by the temperature, and that's Fourier's law of conduction. You solve that in any other fields. In fact, that 1 over L square also appears in physics application as well as electrical applications. For instance, think about x double dot is equal to minus omega square x. This is the equation of the simple harmonic oscillator. And the simple harmonic oscillator has a harmonic solution, cosine plus sine. So in that case, we are not going to reinvent the wheel. We are going to take that equation from Helmholtz and basically find its analog in other fields of science and engineering, in electrical engineering, in physics, and seek the solutions to that equation. And simply, instead of temperature, instead of voltage, instead of hydraulic head, in other fields of science and engineering, you'll find that the equation applies to the behavior of neutrons in a nuclear reactor. Because it's a second order differential equation, we'll need to add two boundary conditions in solving it. And in fact, when we solve that equation, you find that we can determine how the power distribution as a function of space in the nuclear reactor occurs. We'll see that it peaks near the center and reaches zero a little bit beyond the boundary of the reactor. Notice that here the Helmholtz equation assumed steady state, but what about the control of nuclear reactors? The nuclear reactors are controlled as a function of time. So in that case, we cannot ignore that term here, but then we consider the reactor as having no dimension in the X, Y, and Z direction. We call it a point reactor. So that's like looking at the plane on a radar as a point rather than looking at the position of the wings, the tips of the wings, or the tails of the plane. In that case, we solve the equation that's time dependent, and this is a field of what we call reactor kinetics. So we study the behavior of the reactor as a function of time to determine how to control the power of the reactor as a function of time. Here we are going to think about the steady state and how the power is generated in a nuclear reactor. Notice that if you have a partial derivative with respect to time in differential equations, we have to determine what are the initial conditions. But here we only have dependence on the X, Y, and Z. So it's spatial dimensions. And in that case, we have to determine how to determine the boundary condition for steady state conditions of the diffusion equation. And we are going to start solving it in our next lecture. You can have boundary conditions that are determined by the vacuum. In that case, we say that the flux is zero at the outer periphery of the nuclear reactor. And we define in that case a diffusion coefficient as the lambda transport. This is a transport mean free pass. It's a modified transport mean free pass from transport theory. And the diffusion coefficient is nothing than that distance divided into 3. Notice here that the diffusion coefficients would have units of distance. Another type of boundary conditions that we deal with in that type of a problem is that the flux does not vanish really at the boundary of the reactor. You find that the neutron flux peaks at the center of the reactor, and then some neutrons leak outside the reactor. So we call that distance where leakage occurs as the extrapolation length, and that extrapolation length is usually 0.71 the transport mean free pass. So we use that as a boundary condition. If you have two different media, like in heat transfer or in electronics, at the boundary you make the flux at one side equal to the flux at the other side of the interface, and you also make the current or the slope of the curve equal on both sides. If you get a solution and you get a flux, like I had a friend who started getting negative fluxes in some of the calculations, that is not physical. You cannot have a negative number of particles crossing unit area per unit time. So one important condition in our calculation is that the flux should always be equal, larger than 0. It cannot be negative. That's a physical condition. Any solution that has a negative flux should be dropped, even though mathematically it may be correct. And another important boundary condition is that the flux should be finite. We cannot have in the real world fluxes that become infinite. So when you have a solution mathematically that says that the flux goes up exponentially, when we know in real life that it doesn't increase exponentially, we simply drop that equation. That makes a difference between engineers, which deal with real life problems, and maybe mathematicians, which really deal with an abstract world. So in that case, those two boundary conditions will be applied when we solve that neutron diffusion equation in the next lectures. I would like us to remember our calculus. So I'll give you one or two problems to solve in terms of the operators, the gradient, and the divergence and the Laplacian, just to remind you of what we have learned in calculus, and start the next time solving real cases of nuclear reactor. We'll start first with non-multiplying media, and then we will graduate into multiplying media. And in that case, you become privy to the secret of the nuclear age, how to make a nuclear self-sustained chain reaction. I'll go and